So, good evening, everyone. Today we are going to start the next part of the the next set of the questions related to convective heat transfer, and I'm sharing my screen. Today we are going to see the transport coefficients related to heat, mass, and momentum transfer, and then will also see the different relations between the momentum, thermal, and mass boundary layer. So moving on, uh, first I will just give a brief on what are the um, dimensionless numbers or what are the coefficients and all. So firstly, as discussed in last class, Prandtl number is given by nu by alpha. It is this gives the measure of the ratio of momentum diffusivity to thermal diffusivity. So it basically compares the rate of diffusion of momentum to the rate of diffusion of this thermal of heat transfer. Okay, so this also gives the relation. This also tells about the boundary layer thickness of the momentum and thermal, which one is larger, which one is smaller. Okay, so if the momentum diffusivity, I mean if it is if Prandtl number is greater than 1, then the momentum boundary layer will be hydrodynamic boundary layer will be larger, and the thermal boundary layer will be smaller. If it is less than 1, it will be the opposite. Okay, then next is the for uh, for heat transfer, this PR is the one which will decide, this Prandtl number is the one which will decide the ratio between this momentum and thermal diffusivity, whereas for mass transfer, Smith number will decide. Smith number will decide. So this is the mass diffusivity. It gives the relation between the mass diffusivity and the thermal diffusivity. So again, if you want to know the relation between the boundary layer thickness of the mass and thermal, this number is used to give the relation between that. The next is the uh, Nusselt number. Nusselt number is given as resistance for conduction in fluid to the resistance for convective heat transfer. So, what is the resistance for conduction in conduction? So, it is L by Kf into A. And what is the resistance for convection? It is 1 by H into A. So this has the same formula as the Biot number also, but there is a difference in that in Biot number this conduction takes place in the solid, whereas for if you want to measure in fluid, it is the Nusselt number. Okay, and this convection is the heat transfer taking place from the solid to the liquid. I mean at the interface at or at the boundary. So this will give you the Nusselt number. HL by Kf. So this is for fluid. Note that this thermal conductivity is for the fluids. Now same is given for the Sherwood number also. So Sherwood number is the resistance for uh, mass transfer in fluid divided by the resistance for mass transfer from solid to liquid. And this is given by HM is the coefficient for mass transfer. Then DABL is the length. DAB is the diffusion coefficient for mass transfer. Okay. The next is the skin friction coefficient is given as friction coefficient given as tau also it is Also, this can CF is equal to Stanton number into Prandtl number to the power 2 by 3. Now this, sorry, there is no 2 here. This Stanton number is equal to Nu by Re into Pr. Okay. So for heat transfer, it is Nu by RePr. For mass transfer, it is Sherwood number by ReS. So this is the formula. Okay, so we can move on to the questions and will eventually solve with the help of these formulas. So first question is forced air at T infinity equal to 25 degrees Celsius and V equal to 10 meter per second is used to cool electronic elements on a circuit board. Such element is a chip 4 by 4 millimeter. So there is this circuit board. This is the circuit board. It is very long. Okay, located on a 120 millimeter from the leading edge of the board. So the whole distance is of L distance, suppose L or X distance, but the chip which is present on top of it is 120 distance from the leading edge. So if this is the leading edge, then the chip is present here. Okay, this is the chip. Hello, can you see my screen?
Yes.
Okay, fine. So we are solving this problem now. So this is the problem forced air at T infinity equal to 25 degrees Celsius. That means the outside temperature is 25 degrees Celsius and the velocity of the air is 10 meter per second. This is used to cool electronic elements on a circuit board. So this is the circuit board. This thing is a circuit board. One such element is a chip 4 by 4 millimeter located at 120 millimeter from the leading edge of the board. So if this green one is the circuit board and then this is the leading edge, then 120 millimeter from the leading edge is where the chip is present. So this is the chip. Okay. Now experiments have revealed that flow over the board is disturbed by the elements and that convection heat transfer is correlated by an expression of the form NUX equal to 0.04 REX to the power 0.85 PR to the power 1 by 3. So the properties of air is given, nu is kinematic viscosity is given, the conductivity is given, and also the Prandtl number for air is given. Now what they have asked to find out? They have asked to find out the surface temperature of the chip if it is dissipating 30 milliwatt. That means Q is given. It is dissipating this much. Okay, so for this, what we have to do first is, so in such problems where this is given, you always have to find out what is the heat transfer coefficient, okay, or the local heat transfer coefficient, Hx or HL bar. So how do I proceed here? So already the expression for Nusselt number is given. So from here we can proceed. This RE is, the Prandtl number is already given here, 0.703, and RE you have to find out. So for finding out RE is given as Rex is given as L into V divided by mu, the kinematic viscosity, okay. So what is L here? L given is this 120 millimeter, okay. And then V is 10 meter per second, and then mu is 16.69 into 10 to the power minus 6. So L given is how much? 120 into 10 to the power minus 3 into V is how much? 10 meter per second. So all these are in SI units. This was in millimeters, so I have converted into meter, and 10 was meter per second, and this is meter square per second. So all these are in SI units. So just calculate it how much it will come. So are you able to follow this? Please calculate it how much it will come. RE. So this will come out to be around 7 point. Now we have got the value of REX at this location. Now we can calculate what is the Nusselt number. So we can calculate what is the Nusselt number now. Nusselt number was given by 0.04 REX to the power 0.85 Prandtl number to the power 1 by 1/3. So just Prandtl number was given to be 0.703. How much do you get if you calculate this NUX? Please calculate this and tell me how much is NUX. $125.91. Is it the value of Nusselt number? I think you have to calculate. I think you have to calculate again. It's coming something else for me.
Okay, so something wrong in calculation is something wrong, right?
Yeah, yeah. Please try it again. Yeah,
Yeah.
yeah, yeah. So you should get this to be around 477.76. Did you get this number?
Yes. Yes.
Okay. So now how do you calculate H from this Nusselt number? So Nusselt number is given by, I have already shown in the this small brief over this dimensionless number. Nusselt number is given by HL by KF. Here this note that this KF, this is the conductivity of the fluid, not of the solid. Okay. So this NUX is given by HX into L divided by KF. So it is a fluid. Now from here you can calculate what is HX. HX is given by NUX into KF divided by L. So Nusselt number is 477.76 into Kf. Kf is given here as, so for these are the properties of the air. So air K conductivity is given as 26.9 into 10 to the power minus 3 watt per meter Kelvin. So this is also in SI units. This L 120, again 120 millimeter. So 120 millimeter in meters, it is 10 to the power minus 3. Now please calculate this Hx. This 10 to the power minus 3 will get cancelled.
107.09.
Yeah, 107.09. Okay. So what they have asked to find out? They have asked to find out, estimate the surface temperature of the chip. So Q is given, the heat dissipation is given, and you have found out what is H. So you can directly find out now what is the surface temperature. So Q is given by Hx into A into Ts minus T infinity. Okay, so T infinite is given the temperature of the outside surrounding air, that is 25 degrees Celsius. It is already given. Now you have to find out what is this Ts. So Q is given as 30 milliwatt. So let me first write Q is equal to Hx into A into delta T, that is Ts minus T infinite. So this will give us 30 milliwatt. That means 30 into 10 to the power minus 3 watt, right? Now Hx is given as this 107.098 into area. So area is, they have asked to find out what is the surface area of the chip. So what was the area given in the question? That is 4 millimeter by 4 millimeter dimension. Okay. So area is simply 4 into 4, but converting millimeter into meter, it will give 10 to the power minus 3 into 10 to the power minus 3. So it will become 10 to the power minus 6 into Ts minus T infinite is 25 degrees Celsius. Now we have to find out what is Ts. Okay. So how much do you get Ts surface temperature? Are you able to calculate?
Yes, 4.4 multiplied by 10 raised to minus 3.
That is the value for TS.
69.81.
69.81. Okay, but I'm getting something else. This 10 to the power minus 3, it will become, if this goes up, then it will become 10 to the power 3. Then 30 into 10 to the power 3 divided by 107.098 into 16. How much do you get this? So this is around 17 degree, 17.5, this particular thing. And 25 plus 17.5 will give us 42.5 degrees Celsius. So this is the answer. So please check your calculation again. I hope you get the answer. So just let me know you have understood the process or not. That is the main thing here. I mean, getting the answer you'll get anyways.
Yes, ma'am. And
Okay. So we'll move on to the next question. Okay, here, as a means of preventing ice formation on the wings of a small private aircraft, it is proposed that electrical resistance heating elements be installed within the wing. To determine representative power requirements, consider nominal flight conditions for which the plane moves at 100 meters per second in the air. That is at a temperature of 23 degrees Celsius. So we know that as you go above more and more when you fly in flight and all, on top it is the temperature decreases. So it is minus 23 degrees Celsius given for this problem, and has the properties of K is equal to 0.022 watt per meter Kelvin. That means it is of the air, Kf. PR is also given, conductivity is given as 0.72, mu is given, kinetic viscosity is given as 16.3 into 10 to the power minus 6 meters square per second. Now, if the characteristic length of the airfoil is L equal to 2 meter and wind tunnel measurements indicate an average friction coefficient CF bar. So average is given CF bar. Friction coefficient for the nominal conditions. What is the average heat flux needed to maintain a surface temperature of Ts equal to 5 degrees Celsius? So here what they have asked to find out the average heat flux, that is Q double dash of average. So average heat flux means, how do you calculate this? Average heat flux is given by average heat transfer coefficient. Obviously A you don't require, area you don't require because it is the flux. You have to find out the flux. So you don't require area. Then the temperature difference, that is Ts minus T infinite. So Ts is given as 5 degrees Celsius. T infinite is given as minus 23 degrees Celsius. Now only the thing you require to find out this heat flux is this heat transfer coefficient, average heat transfer coefficient you need to find out here. So for finding out this, what are all the information which is given? V velocity of the air is given 100 meter per second. The conductivity is given as 0.022 meter Kelvin. Prandtl number is given as 0.72. Nu is given as 16.3 into 10 to the power minus 6 meters square per second. And the characteristic length is also given 2 meter. And then CF, if the average coefficient friction is given as CF is equal to 0.0025. Now we also know the CF as I have written in the first page. CF is equal to Stanton number into Prandtl number to the power 2 by 3. Okay, what is the formula for this? Is there 2 here? Okay, we'll continue with this only. So CF is given by CF by 2 is Stanton number into Prandtl number to the power 2 by 3, which is equal to Stanton number is given as Nusselt number divided by RE PR Reynolds number into Prandtl number into Prandtl number to the power 2 by 3. So this particular number is known as Stanton number. Okay. Now from here, how do you calculate? How can you calculate this H? Again, it's the same thing. Nusselt number. From Nusselt number, you get the H. So PR is already constant. It is a constant thing. I mean, it is specific property of the fluid. So PR is already given as 0.72. Then what else do you require here is the Reynolds number. Reynolds number you require, so we need to calculate this Reynolds number. RE is equal to again L into V divided by mu. So L is characteristic L length is given as 2 meter into V is 100 meter per second, and nu is also given as 16.3 into 10 to the power minus 6. So if you calculate, how much do you get Reynolds number? So you must get something to the power 10 to the power 7. How much do you get RE? 2 divided by 16.3. 0.122 into 10 to the power 8 or 7. So have you got this RE? Okay, now Nusselt number is given as HL by K. Then RE, PR you can take this here, so it will become 1 by 3. So this is CF by 2, right? So next is CF, how much CF is given as? If you directly take all the values, you get 0.0025 divided by 2 equal to H into characteristic length. L is the characteristic length, so it is given as 2. Then K is how much? 0.022 watt per meter Kelvin. RE is given as 1.2 into 10 to the power 7. And PR is given as 0.72 to the power 1 by 3. So you can, from this, you can just calculate what is h. So please calculate how much is h from here. So you are supposed to get this value 147.8 watt per meter square Kelvin. So from here you can calculate what is Q flux inlet, Q double dash. So you don't require the area here. So direct H into Ts minus T infinity. So H is 147.8 into Ts is given as 5 degrees Celsius and minus of minus 23. So that sign is very important. So this thing will become 28, 147.8 into 28. So how much did you get this? How much do you get this? This simple calculation.
Four one three 8.4.
Yeah. So which one is the option here?
Option A.
Yeah, yeah. So it is almost near to option A. So it will be option A only. So this also you got it right. So from all these questions, what do you get is that the main thing is you have to calculate what is the this either local heat transfer coefficient or average heat transfer coefficient. If you can find all this H, then you can proceed with the next step. I mean, you can solve the problem. So main goal is to find this H in such problem. So next we come to the next question. Here it is given as a circuit board with a dense distribution of integrated circuits, ICs, and dimensions of 120 millimeter by 120 millimeter on a side is cooled by the parallel flow of atmospheric air with a velocity of 2 meter per second. Sorry, I've lost some connection. So here a circuit board is again given with a dense distribution. It has a number of integrated circuits here. So these are the integrated circuits and dimensions of 120 millimeter by this. Each of them has 120 into 120 millimeter square. On a side, then these are cooled by since these are circuits, so this will get heated up, and this heating is they are cooled by this parallel flow, this flow of atmospheric air with a velocity of, so the outside air, surrounding air has a velocity of 2 meter per second. Then from wind tunnel tests under the same flow conditions, the average frictional shear stress on the upper surface is determined to be 0.0625 Newton per meter square. That means tau is given, shear stress, okay. This is 0.0625 Newton per meter square. What is the allowable power dissipation from the upper surface of the board if the average surface of the IC's integrated circuits must not exceed the ambient air temperature by more than 25 degrees Celsius? Okay, so what they have asked the power dissipation. That means they have asked Q on the upper surface of the board if the average surface temperature must not exceed the ambient temperature by more than 25. That means if average temperature, surface temperature is Ts and ambient temperature is T infinity, then this should not exceed 25 degrees Celsius. Okay, so we can consider they have given the temperature difference delta Ts. If you consider delta T as 25 degrees Celsius, then you can proceed. So here they have given this delta T, the different temperature difference. Now air properties are given. Rho is the density is 1.61 kg per meter cube, 1.161. Then the Cp specific heat is given as 1007 joule per kg Kelvin. Okay. Joule per kg Kelvin. The Prandtl number is given as 0.707. So again, for this, how do you proceed in such questions? You need to find out what is this H, right? So for finding out what is this H, you need to uh, see what else is given here. The tau is given, the shear stress is given, the air properties are given, and fluid properties and the dimensions of this circuits. So we have a relation which connects the heat transfer coefficient with this shear stress as CF equal to CF divided by 2 is equal to Prandtl number into Prandtl number to the power 2 by 3. Okay. So Prandtl number is given as, so here also you need to find out. Okay, I'm reading the question again. So a circuit board whose dimensions are given. Circuit board has a dense distribution of integrated circuits whose dimensions are given 120 into 120 millimeters square. On the side is they are, since they get heated up, they are cooled by a flow of atmospheric air with a velocity of 2 meter per second. So air velocity is 2 meter per second. From the wind tunnel test under the same flow conditions, the average frictional shear stress on the upper surface is determined to be 0.0625 Newton per meter square. That means the frictional stress, that is tau, is given as 0.0625 Newton per meter square. What is the allowable power dissipation from the upper surface of the board if the average surface temperature of the eyepiece must not exceed the ambient air temperature by more than 25. That means if the average surface temperature is Ts and the ambient air temperature is T infinity, then the difference of that should not exceed 25 degrees Celsius. That means here the delta T is given. So you can take this, you can consider this delta T temperature difference as 25 degrees Celsius. Then what they have asked to find out, they have asked to find out the allowable power dissipation from the upper surface. That means this Q, power dissipation. Okay. And then they have given some properties of air, density they have given, specific heat, Prandtl number they have given. So again, in this case, you need to find out H, and how do you relate this heat transfer coefficient with this, what else are given here. So we have seen that the shear stress is given. Then how do you relate this shear stress with the H, heat transfer coefficient, is this formula again. So CF is given by tau divided by rho into uh, U infinity square divided by 2. This whole one is CF. Okay. So this into half is equal to Stanton number into Prandtl number to the power 2 by 3. So again same thing, Nu by Re PR. Directly you can write PR to the power 1 by 3 here. So you must have understood how this came, this 1 by 3. So we have this tau. We know this rho is given as 1.161 kg per meter cube. U infinity is also given. It is the velocity of the atmospheric air, that is 2 meter per second. And then Nusselt number is given as HL by K, from where H you need to find out. L is given as uh, okay, you can also here Stanton number L is also not given here. So but K is given. Is K given here? K is also not given, right? This. So all these are not given. So we need to find out another way how to find this out. So how do you proceed with such problem is Stanton number is given as Nu by REPR. Alright. Now if you break this RE, Nu is given by HL by K. RE is given by RE is given by rho VL by mu. So Reynolds number is given by characteristic length into velocity into density divided by the, sorry, this is dynamic viscosity, right? If you, dynamic viscosity is given by, so this should be mu. So if you write in terms of kinematic viscosity, then this L will also go away. Then below you will directly get the kinematic viscosity. Okay, then into Prandtl number. So from here you can cancel out this L. L you can cancel out. Then you get H. Prandtl number is also given as mu by alpha, right? Then what is alpha? Okay, you have to break this Prandtl number also. So then it will become, how do you write this Prandtl number? It's mu by alpha. Then mu is given as mu by L and alpha is K by rho Cp, right? So what was the formula of Prandtl number? Sorry, I'm extremely sorry. This is mu by rho. So mu by rho is mu by rho. Okay. Mu is equal to mu by rho. So this will also get cancelled out. So what do you get in this whole? This L will get cancelled. Then H by K will also get cancelled here. Then H divided by rho V. Mu will also get cancelled. This rho already got cancelled. Then Cp. So this is the final formula for this Stanton number. Okay, H divided by rho V Cp. Now from here you know rho V is given, Cp is also given. V is given, V is also given, Cp is also given. Okay, so now you can find out how much is this H. So what we have done in this question, did you understand? So in the previous question, CF, directly we could find out, I mean, just find out RE, and then we could directly, since all these values were known, L, K, and you just needed to find out what is RE, then you could directly substitute all these values and you could get this H. Okay, but here we don't know anything. From Nusselt number, we don't know L, we don't know K. Okay, we don't know anything from here. So what we did is that we just substituted the formula, direct formula for all these numbers, for Nusselt number, Reynolds number, and Prandtl number. Okay, so Nusselt number is given by HL by K, this on top one, and Reynolds number is given by rho VL divided by mu. Okay, then Prandtl number is given by mu by rho into rho Cp by K. That is mu. This is, in short, you can write mu by alpha also. So if you break down that, we get this. Now we also directly we can write mu Cp by K. That is also Prandtl number only. So rho you can cancel, and then L you cancel, then this mu also you cancel. Then what remains for Stanton number is this H divided by rho V Cp. Now you know all this, so you can directly substitute. Now tau divided by rho u square by 2 into 2 is equal to, that was Stanton number into Prandtl number to the power 2 by 3. So instead of St, we can write this Prandtl number. Prandtl number is already given, so we don't need to worry about that. It's given as 0.707. So 2 you cancel, rho you cancel, and this v and u they are same. Okay, so one u gets cancelled. Now you can directly calculate what is, sorry, you have to calculate h, right? So you can calculate what is h. U infinity is given as 2 meter per second divided by Cp. Cp is how much? 1007 joule per kg Kelvin. So all these are in SI units only. Please calculate how much is this H.
Uh, 1.7 multiplied by 10 raised to minus 3.
Something else. H is given by 0.0625 into 1007 divided by 0.7 to the power 2 by 3 into 2. So have you calculated this? You have to calculate this. You must be doing something in calculation, some mistake in calculation. I'm getting 39.65.
Yes, yes, sir, 39 watts.
Huh. Okay. So what was the question given? The question was to find out this Q, right? Heat, not heat flux, Q only. Heat only they have asked to find out. So we know H, we know area also, 120 into 120 millimeter square, and uh, temperature difference, which is given as 25 degrees Celsius. So I'm writing here Q is equal to HA delta T, right? So H is 39.65 into area is 120 into 120. So millimeter square into meters, if you convert into meter square, it will be 10 to the power minus 6 into delta T is 25. So how much is Q? Just calculate this Q here. It is coming to be around 14.27 watt. So last one is the correct option. You got Q?
Yes, sir.
Okay. We'll move to the next question. Here, they have asked for flow over a flat plate with an extremely rough surface. Convection heat transfer effects are known to be correlated by the expression as shown in the figure. That means this NUX is equal to 0.04 REX to the power 0.9 and airflow at 50 meter per second. What is the shear surface shear stress at x equal to 1 meter from the leading edge of the plate? So U infinity is given 50 meter per second. Then x is, I mean the length is given as 1 meter. Then the temperature T infinity is also given. Air temperature is given 300 Kelvin. Now properties of the air is given. New the kinematic viscosity, Prandtl number, and the uh, density. So what is the surface shear stress? Here again you need to find out what is this tau. So how do you find this tau? It's not W, it's surface shear stress. So it's Ts. Okay. Okay. It's the same thing only. So how do you find out this Ts? Okay, this Nusselt number is given in the question as 0.04 REX to the power 0.9, Prandtl number to the power 1 by 3. So we substitute in this NU, so CF, or this 2 and this 2 you can cancel out. So directly you can write tau s by rho u square, tau s divided by rho infinity square is equal to Nusselt, Nusselt number was given as 0.04 REX to the power 0.9, Prandtl number to the power 1 by 3. Okay, and below is REPR and on top is PR to the power 2 by 3. So in this equation we see PR to the power 1 by 3 and PR to the power 2 by 3. If you multiply this we get PR to the power 1. So directly we can cancel this with this PR. Okay, then REX and REX to the power 0.9. How do you write this as? REX to the power 0.9 minus 1 we get as minus 0.1. So that is, now it is much reduced. It's a very simple form You can directly calculate this tau s as rho u infinity square into 0.04 Re to x to the power minus 0.1. So how much is rho given? 1.16 kg per meter cube. U is given as 50 meter per second. This square into 0.04 Rex. Rex is not given, so you have to find out the Reynolds number. L into V. L is this X, that is 1 meter. V is, or U is this 50 meter per second, and divided by nu. Nu is how much? 15.89 into 10 to the power minus 6. 4 to the power minus 0.1. Again calculate this. Calculate it very carefully, okay? Just don't, here also 50 is there, here also 50 is there, then don't mix both, because here it is, this 50 has a power of minus 0.1. So if I calculate this, it is coming around 116 into 50 divided by 15.89. So this is coming to be around 0.224. So if you multiply this, both of this, how much do you get? 25.98 Newton per meter square. So did you get this 25.98?
Yes, yes.
Okay. So they have asked to find out this only, tau. What is the shear stress? What is the surface shear stress at this? So if they ask you to find out Q and all, you can find out the H. Here you don't need to find out the heat transfer coefficient, because you don't need to find out the Q is not asked here. So anyways, if they ask you to find out Q, then definitely you need to find out what is the heat transfer coefficient. Okay, for fully developed turbulent flow in pipe with heating, the Nusselt number Nu varies with Reynolds number Re and Prandtl number PRS. Do you know this? How much it is? This has not yet come in the lectures yet. I mean, for week 5, maybe in week 6 you might get. So B is the answer here. For turbulent flow, you need to know this, for which case For laminar flow it is something else, for turbulent flow it is something else. So you need to know under which condition you are finding out. So that is very important. So under this is Nusselt number is given, it varies with RE as 0.8 and PR to the power 0.2. Okay, for heating. Okay, for heating is the case. There are many cases. So in this it is, I'm telling you, for this it is B only, 0.8 and 0.2. Okay, the next is, which one of the following number represents the ratio of kinematic viscosity to the thermal diffusivity? Can you tell this? This is very easy. Which one of the following number represents the ratio of kinematic viscosity to thermal diffusivity? Kinematic viscosity means nu, thermal diffusivity is alpha. So which number gives this? Which of this number gives? So I had already made a mistake also in that previous to previous question regarding this. So this was a PR, okay? Nu by alpha. That means Prandtl number. Prandtl number is given by nu by alpha. Nu means nu. This is kinematic viscosity. This is dynamic viscosity. So how do you relate this to both the viscosities? Kinematic is given by dynamic viscosity divided by the density, and alpha is the thermal diffusivity. It is given by K by rho Cp. So you know what is thermal diffusivity, right? It is K by rho Cp. That means the ratio of this conductivity to the how much the object has the capacity to store heat. So diffusivity by storage capacitance. Okay. So this is the alpha. Then if you cancel this, then you get mu Cp by K. So you can either write like this or you can write like this also. Okay. This is Prandtl number. So Prandtl number will relate you, I mean, how much the kinematic viscosity is more. Or I mean, how much the relation between kinematic viscosity and thermal diffusivity. Means how much the you can, this can also compare the boundary layers. Okay, different boundary layers. If PR is greater than 1, then what happens? If PR is less than 1, then what happens? All these things you get. So if it is greater than 1, that means the kinematic viscosity is more. Okay. Then the hydrodynamic boundary layer is larger than the thermal boundary layer. If it is less, then it is just the opposite. Okay, so like this you get, this is the significance of Prandtl number. And then next question is experimental measurements of the convection heat transfer coefficient for a square bar in cross flow yielded the following values. Okay, H1 is equal to 50 watt per meter square Kelvin when V1 is equal to 20 meters per second. H2 is 40 when V2 is equal to 15. Now assume that the functional form of the Nusselt number is Nu is equal to C into Re to the power m Pr to the power n. Here C, m and n all are constants. Okay. What will be the convection heat transfer coefficient for a similar bar? That means H. Suppose H3. H1, H2, then this is H3. Similar bar with L equal to 1 meter when V is equal to 15 meter per second. So V's velocity is given and L length is also given. Okay. So in that case, what happens? So first of all, whatever they have given, from there we need to extract what we can do. Okay. Nu is given as CRE to the power M PR to the power N. So from here we see that C is also constant. Okay, this Nu can also be written as H bar L divided by K. Now from here, what are all the constants? C is constant, M is constant, N is constant, PR is also constant because um, the both the objects are placed in the same environment. Okay, so PR is also constant. This is also constant. Then even K is also constant because again the same thing. This is the property of the fluid. So the same they are using the they have not changed the fluid. That means K is also constant. So from here you get H L is proportional to rest all are constant. So you can write now in RE is LV rho by nu. So from here again nu is constant, rho is constant, and this both L and V are varying. So LV to the power M, PR is constant, so you don't need to write. So from all these, you can directly write this thing. If you remove all the constant, you can just write proportion. So H into L is proportional to L into V to the power M. Okay. So we can write this as proportion. That means H1L1 is equal to, or you can write H1L1 divided by H2L2 is equal to L1V1 divided by L2V2 to the power M. Now in the first case, they have not changed the geometry. Okay, they have not changed the geometry, so L remains to be constant in the first case. First case means this two. So L, they will cancel out. It is 0.5 anyways for the first case. So H1 divided by H2. H1 is 50 by 40 equal to V1 divided by V2. 20 by 15. Now from here we can calculate what is M. So this comes out to be, M comes out to be around 0.7775. So you can write 78. Okay. Now they have asked to find out the third heat transfer coefficient for similar bar, but they have changed the dimension. That is L equal to 1 and V is equal to 15. So you can, among these two, you can take any one as the reference. So maybe first one only. The second one you can take. You can write as H2L2 divided by H3L3 L2V2 L3V3 to the power M. H2 is 40, L2 is 0.5, H3 into 1 is equal to 0.5 into both are 15, right? To the power 0.78. So how much do you get this? This is 20 divided by H3 bar. This is equal to 15, 15 you can cancel. 0.5 to the power 0.78. How much this will become? So H3 bar is equal to 20 divided by 0.582. So it is 34.36 or 34.4 almost. So first one is the answer 34.3. Okay, so now we move to the next question. So the next question says the defroster of an automobile functions by discharging warm air on the inner surface of the windshield. To prevent condensation of the water vapor on the surface, the temperature of the air and the surface convection coefficient T infinity I, T, H I must be large enough. That means the temperature. So to prevent condensation, the temperature of the air should be high so that there is no condensation. And also the surface convection coefficient, that is heat transfer rate, that also should be high. That must be large enough to maintain a surface temperature TSI that is at least as high as dew point. Why it is higher, as high as dew point? So that it does not condense. Okay, consider a windshield of length L equal to 800 millimeter and thickness equal to 6 millimeter. So that windshield has length as 800 millimeter, that is 0.8 meter, and thickness as 6 into 10 to the power minus 3 meter. In driving conditions for which the vehicle moves at a velocity of v equal to 30.8 meter per second in ambient air at, so T infinite is also given, that is outside temperature is 15 degrees Celsius and velocity, outside velocity is 30.8 meter per second. From laboratory experiments performed on a model of the vehicle, the average coefficient on the outer surface of the windshield is known to be correlated by an expression of the form NUL is equal to 0.03 REL to the power 0.8 PR to the power 1 by 3. Okay, then air properties may be approximated as K is equal to 0.023 watt per meter Kelvin, and nu, this is nu, okay. Kinematic viscosity is given as 12.5 into 10 to the power minus 6 meter square per second, and Prandtl number is given as 0.71. If TDP, that means T dew point temperature is 10 degrees Celsius, and T infinite I, that means the inner temperature inside of the windshield, it is 50 degrees Celsius. What is the smallest value of HI? Convective coefficient required to prevent condensation on the inner surface. So, to find out what is the HI required to prevent condensation on the inner surface, assume glass conductivity as Kg is equal to 1.4 watt per meter Kelvin. Now, here the whole thing can be summarized as the since inside, outside, and all conductivity of the glass, and this coefficients of inner and outside all are given, you can summarize it as the 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 resistance circuit diagram which we have drawn in conduction heat transfer. So you can simply simplify it like this. So how many resistances are there? There is this outside resistance. If this is T infinite I, this is T infinite outside, this is inside, this is outside, then this is inside 1 by H I, it is 1 by H naught, okay, and this is L by K, that means L is here thickness, okay, T, directly you can write T also, divided by Kg. Here the conductivity is of the, this due to conduction, so it is, we need to take the glass conductivity, okay. Then this temperature is TSI, where is it given? So it is given as um, TSI and TS naught. Anyways, so if I write it here, by H naught, this is 1 by HI, this is T by H, this is TSI. So at steady state, we can consider that if it is the steady state, then we can write like this: the heat transfer from at each point is equal, okay. That means if I consider this T, T infinite minus TSI divided by 1 by HI, this is equal to, here you can write TSI directly considering this whole one, so that is also equal. So TSI minus T infinite O is given by T by kg plus 1 by H naught. So from here, what do we know? We know T infinite naught. We know the outside temperature, 15 degrees Celsius, and then we know the inner temperature and also TSI. TSI you can consider as at least as high as dew point. So dew point is given as 10 degrees Celsius. You can consider TSI as the 10 degrees Celsius. So from here, 15 minus 10. So it's 15. 1 divided by HI. We don't know HI. So HI we need to find out. And then TSI is, sorry, it's we don't know H naught, we don't know HI. Okay, so how do you find out this H naught? We find it out by from Nusselt number. Since all the properties from the outside one is given, right? L is L, we know K also, that K, this K is of fluid. Okay, that is fluid, that means outside fluid it is given, air properties it is given. That's why we are calculating Nusselt number for the outside. So that K is given as 0.023 watt per meter Kelvin. Also it is given as, okay, uh, Nusselt number is also given as 0.03 into REL to the power 0.8. Also, they have given this outer surface windshield is known to be correlated by the expression. So this is for the outside air. So REL to the power 0.8, PR to the power 1 by 3. Okay, now it's not. So KF by L into 0.03 into RE is L into V divided by nu to the power 0.8, Prandtl number to the power 1/3. So Kf is 0.023 into 0.03. Now L here also L, here also L. So L is 0.8 to the power. If we subtract this minus 1, then it will give 0.2 into V's velocity is how much? 30.8 divided by nu. Nu is also Given is given 12.5 into 10 to the power minus 6. So this to the power 0.8 into Prandtl number is how much? 0.71. Okay, so you need to calculate this. How much it comes? Minus. Comes out to be around 64.9 watt per meter square Kelvin. So if we substitute it here, we get as 40 into HI. Calculate, you get, I'm not calculating the whole one, so if you calculate it, you get 38.35 watt per meter square Kelvin. Okay, so this is 38.3. That is the third option. So the next question is, an object of irregular shape has a characteristic length of L equal to 1 meter and is maintained at a uniform surface temperature of Ts equal to 400 Kelvin. So it has characteristic length of 1 and surface temperature is 400. When placed in atmospheric air at a temperature of 300 Kelvin, moving with a velocity v equal to 100 meter per second, the average heat flux from the surface to the air is 20,000 watt per meter square. If a second object of the same shape but with a characteristic length of L equal to 5 meter is maintained at a surface temperature of 400 Kelvin, is placed in atmospheric air, same 300 Kelvin, what will be the value of the average convection coefficient if the air velocity is 20 meter per second? So, uh, first thing we can write are for the first, we can consider, we can start calculating the Reynolds number for the first object and second object. Okay, I'll write it as REL, comma 1. For the first object, it is VL by nu. So it is V is given as 100 meter per second into L is 1 divided by nu. Nu is not given, so it's 100 by nu. And for second, Reynolds number for the second object is V is given as 20 meter per second into L. Its characteristic length is 5 divided by nu. So again it is 100 divided by nu. So both the Reynolds number are coming same. Now they're placed in the same environment. So the fluid characteristic can be considered to be same. Okay, that means nu is constant. Whatever is the nu of, maybe they're kept in air, they're placed in atmospheric air. So nu of air will remain constant. Okay, so we can write as both the RE are same. Okay, if nu will remains constant, then REL comma 1 is equal to REL comma 2. So if this is the case, and also since Prandtl number is also a characteristic of the surrounding air, so this will also remain constant. So if RE is also constant, Prandtl number is also constant for both the objects, we can say the Nusselt number is also constant. So Nusselt number is a function of actually RE and PR. Now both RE and PR, both of them are coming constant. So we can say NuL1 is equal to NuL comma 2. That means H1L, Nusselt number is given by H by HL by K. H2L2 by K2 or K1 you can consider. But this K is also a property of fluid since it is Kf. So this is thermal conductivity of the fluid. That means this will also remain constant. This is also a property of the fluid. So this will also remain constant. So we can simply write H1L1 is equal to H2L2. So what they have asked to find out? They have asked to find out what will be the average value of the average coefficient, convection coefficient, if the air velocity is this. That means H2 you need to find out. H1 is given as, so H2 you can find out as H1 into L1 divided by L2. H1 is given as, okay, they have not given H1, but they have given the average heat flux, that is Q they have given. Okay, so how can you find out H from there? So Q divided by A is given. This is H Ts minus T infinity. So this was 20,000 is equal to H1. So this thing you can bring here. Ts minus T infinity. Ts is given as 400 minus 300. T infinity is 300. So 400 minus 300. So H1 bar is equal to divided by 100, right? So it will become just 200 watt per meter square Kelvin. Okay, so here if we substitute the value of H1, these all are average values. So 200 into L1. What is L1? L1 is 1 meter and L2 is 5 meter. It will come out to be 40 watt per meter square Kelvin. Okay. So have you understood this question? Whoever is present here. Okay, I'm just telling you in brief. So they have two objects. Okay, one has characteristic length of 1 meter and another has a characteristic length of 5 meter. Characteristic length is given and both of them are placed in atmospheric air. Okay, the atmosphere is not changed, the surrounding is the same. If the surrounding is same, then there are few parameters which remains constant. That is this mu is dynamic kinematic viscosity. Kinematic viscosity is also a property of the fluid and Prandtl number is also a property of the fluid. They will not, if the fluid is not changed, they will also remain same. They will also not change. Then surface temperature is given for the first object 400, outside temperature is 300, outside temperature is anyways it will not change. And for the second object also it is the same, surface temperature is 400, outside is 300. So now they have given the velocity at which the air is moving, and in the first case is 100 and the second case it is 20. So here you can, if you have to calculate the H, they have asked to find out the average convection coefficient and they have given you the average heat flux. So how can you find whatever information is given? So you have to find H from Q only as a function of Q or from Q. So H is given by Q divided by A into Ts minus T infinity. But they have already given the flux, that is Q by A they have already given. Then from here Ts is also given, the surface temperature, and also T infinity, that is the air temperature they have given. Then uh, another functionality of H is this Nusselt number. Okay, so Nusselt number, if you want to calculate, Nusselt number is a function of Re and PR, Reynolds number and Prandtl number. So Reynolds number you find out for the first object, V into L divided by nu, you get 100 by nu. For the second object is also 100 by nu. So since nu is constant for both, we can consider this Reynolds number is same for both the objects. Now Prandtl number will also not change, so it will also remain constant. So since both are constant, Nusselt number will also remain constant. Now if you break down this Nusselt number, it is HL by K, HL by K. So you can simply write it as H. You can compare both H1 L1 divided by K1 is equal to H2 L2 divided by K2. And K, this K is also conductivity of the fluid. So this is also a property of the fluid. Again, this will not change. So both of them will get cancelled out. Then you can directly write this. Then whatever information is available to you, from there you can find out H1. Then if you have, once you have this H1, you can directly calculate this H2 also. L1, L2 both are given. Then H2 you can find out. Okay, clear? Okay, are you able to solve assignment questions? Assignment questions, that those are weekly updated. They have, and you need to submit those also. Are you able to solve those questions? Are you following the class? Okay, fine. So today we'll stop here. So I hope you have understood this, and then next class we'll continue with the next set of questions. Okay. Yeah. So thank you for today. We'll continue in the next class.